Okay, so we just renormalized the coupling. Now we have to do the same for the 2-point function, so let's now renormalize that. So next we renormalize the 2-point function. So how do we do that? So the truth is, this actually involves a kind of interesting wrinkle, because what we now want to do is understand how the pole shifts in perturbation theory. Remember, the 2-point function has a pole. In the free 2-point function, it looks like I over p squared minus m squared. We now want to understand how the pole moves as we go to higher orders in perturbation theory. Okay, it turns out to do this, we're going to need to sum an infinite set of Feynman diagrams. And it should be clear why. If you have a function like this, if you add just a small correction to it, it's not going to change the pole. To understand the shift in the pole, we do have to sum an infinite number of Feynman diagrams. So let me now explain how that's going to work. So first of all, to order lambda to the 0, we have the following result for the free 2-point function. Let me just write this down again. Excuse me. Equals to dfp, where this is the free propagator. So this is in the free theory. Now, to order lambda to the 1, we have some other corrections to this, right? So at order lambda to the 1, if I was to donate this by just the free propagator line, order lambda to the 1, we have new diagrams. So for example, there's a diagram that looks like this. Okay, momentum P going in here. And there's also a diagram that comes from the counter term Lagrangian. And that diagram looks like this. And if you've forgotten what the counter term Lagrangian is, you can go scroll back upwards and take a look at what those terms are. Okay. And again, there's momentum P flowing into here. So I am going to call these two terms together minus I sigma of P. Okay? So minus I sigma of P is these two terms. Now, in fact, minus I sigma of P is a name that I'm giving it because this is conventional. There's a better name for this. The right way to think about the sum of these two diagrams is as a set of 1pi diagrams. So what does 1pi mean? 1pi stands for one particle irreducible. See, my head is getting in the way. Okay. And a diagram is 1pi if you can't break it into two by cutting a single line. Okay. So this is best understood through some examples. So for example, let me draw something complicated. Let's say this diagram here with this and then this. This is 1pi because I cannot break it into two pieces by cutting a single line. On the other hand, this diagram is not 1pi because if I cut this line, then I break it into two. So you can see that there's a sense where a 1pi diagram, it's kind of the unit cell of the propagator. I'll explain what this means in a minute. But it's the unit cell, it's like the simplest possible unit that makes up the propagator. All right. And in particular, this concept is developed a little bit more on problem set 2. So you should take a look at that if you want to understand a bit more of that. So to come back to this language, the right way to think about these two diagrams here is that these two diagrams that I've drawn here are the order to the lambda 1 correction to the 1pi irreducible diagrams. Okay? The only diagrams at order lambda to the 1 that contribute to the 1pi diagram are these two. Okay, so now that we have this name, let's now consider adding these two things up to actually calculate the answer. So what do we do? So first of all, we have the free propagator. Next up, we should add those two things together. Okay, so this is the 1pi diagrams from above. So what do we have? So let's see if this is the free propagator df of p. Then we now take df of p and multiply it by this new correction. So remember, I called the correction from the 1pi thing itself I sigma of p. And then I also have an extra factor of df of p here coming from this guy. And I should emphasize, by the way, that here we're not doing LSZ, so we're not amputating the propagators. That's why I'm keeping all of the factors of df. So I'm not amputating anything. Okay, now we could stop here, but that won't actually give us the information that we need. Notice that we can now keep going, right? So for example, we could consider this contribution. And consider this contribution, where each of these is the 1pi thing, and so on and so forth. And we can now consider summing up this infinite sum of Feynman diagrams. Okay. Now this sounds hard, but luckily it's a geometric series, so actually it's not hard at all. The full sum takes the following form: df of p times the sum, n goes from 0 to infinity, of minus I sigma of p df of p, and the whole thing here is raised to the power n. Okay? And you can see why every time you add another unit cell, you add a factor of sigma of p and a df. Okay? So that's the sum, and by the normal rules of geometric sums, we can just do this, and what we find is df of p times 1 over 1 minus the thing that we're raising to the power. So it is I sigma of p df of p. Now, if you plug in the fact that df of p is I over p squared minus m squared, this whole thing just becomes I over p squared minus m squared minus df of p. Okay. So this is the summed up propagator. So now, you see, this has done what I claimed it would do. By summing up this infinite series, we have actually seen how the pole shifts. Oh, excuse me, this is wrong. I mean, 1 minus over p squared minus m squared minus sigma of p. Okay, now it's correct. And you see, we have done what I claimed that we were going to do. By summing up this infinite series of diagrams, we have seen that the pole shifts, and the way in which the pole shifts is exactly by this thing sigma of p. Okay? And now you can calculate sigma of p to whatever order and perturbation theory you like, and you'll see how it contributes to the location of the pole. Okay, so now let's think back to what the propagator means. We can see here that actually sigma of p evaluated at p squared over m squared tells you the new location of the pole, and so this is the shift in the mass. Okay. And similarly, you can show that d sigma of p over dm squared, dp squared, evaluated at p squared equals to m squared, this turns out to be the shift in the residue. And I'm not going to show that here, but there's a problem that works you through it on problem set 2. So take a look at that. Okay. And now we're ready to go and impose our renormalization conditions. If we go backwards, remind ourselves what those were. The renormalization condition was precisely that there's no shift in the mass, and that the coefficient of the residue, the coefficient of the pole does not change. And so in terms of sigma, what that means is that we want that sigma at p squared over m equals to m squared equals to 0, and also that d sigma of p, dp squared, at p squared equals to m squared equals to 0. So this is the renormalization condition written in terms of sigma. Okay. Okay. So now let's finally calculate the diagram. Okay. So what is the diagram? Well, here they were. We had these two pieces here. So we know how to do this guy. The first piece just gives us that I sigma of p squared equals 2 minus I lambda, a factor of 2 from a symmetry factor, and a d4k, 2 pi to the 4th, I over k squared minus m squared. And then there's a contribution from the counter term Lagrangian, which you remember looked like that. That contribution is I p squared delta z minus delta m. Okay. And now notice the interesting thing. This guy here came from the loop diagram, which looked like this. But actually, the momentum coming into this is p. And this loop diagram doesn't actually care about the amount of momentum p flowing into here. It's completely independent of p. So that means this whole thing here is just a constant. Okay, so this is just a constant. So that makes the whole thing much simpler. Okay. In fact, we can immediately see that we can satisfy the renormalization condition here if we just set delta z equal to 0, because the only thing that depends on p is this term over here. And we should also set delta m equals to negative this thing to cancel it out. So if we have delta m equals to minus lambda 1/2 integral d4k over 2 pi to the 4th I over k squared minus m squared, then this choice of the counter terms, delta z and delta m, satisfies this renormalization condition. Okay, so that's pretty much it. We're done. Okay. To be fully complete, I should probably calculate this, this counter term. I should probably do this loop integral and figure out what this is. I'm not actually going to do it. It's not very illuminating, and this really depends, crucially, on what kind of cutoff we use. It's very cutoff dependent. And in particular, if we use a hard cutoff like we did earlier, then we get something like delta m goes like little lambda, capital lambda squared. It's a quadratic divergence, okay? There's not much that, that we have to do there. Okay. Okay, now with these choices, we can see that sigma of p squared is in fact exactly 0. Okay. Now, this actually is the analog of the matrix element that we calculated before, where I, S of t and u equal to some complicated function of s naught, t naught, blah, 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 s and u. This is the analog of that for the 2-point function. The fact that it's so simple is kind of just an accident. Okay, there's nothing deep going on here. In particular, this could have had a finite dependence, a finite complicated dependence on p. Okay, and just to prove to you that this does actually happen, I encourage you to take a look at problem 10.3 on page 345 of the textbook of Peskin and Schroeder. In particular, there you can work out an example where this is actually much more complicated, and you can really see that you get a non-trivial dependence on p after carrying out the renormalization procedure. Okay, so that concludes the renormalization of lambda phi to the 4th theory at 1 loop order. Okay, we calculated a bunch of counterterms, and we figured out what they should be, and we made sure that everything was finite afterwards. Okay, we're done. You can see that in this example, renormalization is really just a kind of careful bookkeeping, right? You add some counterterms, you make sure you have the right set of counterterms, you make sure everything works out. Now, you should really have the following question. Is this always true? Is renormalization always just bookkeeping? For what theories does it work? And are there theories for which it doesn't quite work? And that is a topic of the next video. Okay? Where we'll understand what theories you can renormalize in this way and which ones you have trouble doing it for.